welcome to the section 5.4 notes, which is about still the multiplication rule, but this time we have to have the general multiplication rule because we are going to be dealing with dependent events. Which dependent events, they bring up this idea called conditional probability, which is that the probability changes under some condition. And that's already the meaning of dependent events, which is that they are the condition under which the probability of some other event will change. And so we have a notation for it. It is pretty straightforward to do. It's just that we have a new notation to try to interpret here, and you write it with this vertical bar. This is saying the probability of f given e. That's how you pronounce this one out loud, like this. But what it means is that event e has already happened, and we're expecting that the probability of f, if it's dependent on e, then this is going to be something different. I could write it like this. If the probability of f given e is the same thing as just the probability of f, that means that e does not affect the probability of f, because we're saying e already happened. So what's the probability of f now? If that's the same as just the normal probability of f anyways, then this means that e and f are independent. And we would have, if I put a not equals right here, then that would be the situation where they are dependent. And so we'll figure out here some independent versus dependent situations, but when we're talking about dice rolls, we can just use this example to try to understand what the notation means. This is a probability to roll a 3 given that you've rolled an odd. So when we're trying to calculate this probability, we only need to look out of the odd ones. It's going to be something out of the number of odds, because it's already given that an odd was rolled. Now we want to know what's the probability that it's a 3. And so there are just 1 3s that we can roll. 1 out of the number of odds. There are 1, 2, 3 odds. And so it's a 1/3 chance that we rolled a 3 given that we rolled an odd. And then here the probability to roll a 2 given that we rolled an odd. We're looking out of the number of odds. This becomes our sample space essentially that we're dealing with, because we know that we rolled an odd. What's the probability that we rolled a 2? There are no 2's out of here, so it's a 0. 0 chance to roll a 2 given that you rolled an odd. The probability to roll a 1 given that we rolled a number less than 5, that's these 4 are less than 5. So it'd be 1 out of 4. One of them is a 1. 4 numbers are less than 5, so 1 out of 4 chance to roll a 1 given that we rolled a number less than 5. And then the probability to roll a 6 given that we rolled a number that is a multiple of 3. Well, 3 and 6 are the only multiples of 3, so it's a 1 out of 2 chance. There's also a 1/2 chance to roll a 3 given that we rolled a multiple of 3, and the other ones would be 0 probability to roll those ones given that we rolled a multiple of 3. Now we can do some examples that have to do with replacement. Whenever you see these words, these are indicating or letting us know whether we are dealing with dependent or independent events, because if we roll with replacement, or not a roll, but I'm thinking about drawing, like there's examples of drawing marbles out of a bag with or without replacement. Here, drawing from a standard deck of cards with or without replacement. If we put the cards back after we draw them, then that means that the probability is going to not change on the second draw, so they're independent events. For example, the probability that all 3 cards that we draw are kings, and we're doing with replacement, so we draw a card, put it back, draw another card, put it back, and each time there's a 1 out of, well, let's see, there are actually 13. I was going to say 1 out of 52, but there's actually 4 kings. It only needs to be a king, so there are 13, a 1 out of 13 chance to draw a king. And since we're doing with replacement, we should multiply on the next one the probability to draw a king again, which is 1 out of 13, times the probability to draw a king again is 1 out of 13. We just multiply these, and we would get 1 out of whatever is 13 cubed. Let me get my calculator. And here 1 out of, I'm just going to go 13 cubed like this. I think this should do it for us. It's very unlikely, of course, to draw 3 kings in a row. And it's 4, I'm going to call it just 4.55. It was, oh, there we go, 4.55, and it's times 10 to the negative 4th. So I think a better way to write it would be, go ahead and go 1, 2, 3, 4 decimal places and 0.000. I'm just going to round it to 5 right there. It's customary for the probabilities to be 4 decimal places, so this would be the correct probability for that one. Now, what about the probability that all 3 cards are kings that we're drawing out of this deck if we're sampling without replacement? So on the first draw, there's a 1 out of 13 chance to draw a king. And then we're looking for what's the probability to draw a king again, but we don't put this king back, the king that we drew. So now there are 3 kings left out of, we already drew one of the 52 cards, so now there's only 51 cards left. This 3, this is the number of kings remaining. Oops, number of kings. Number of cards remaining since we already drew one. And so that should be our probability right there, 3 out of 51. And now we drew a king again. We don't put it back because it's without replacement. So now there are only 2 kings left in there. Out of the 50 cards that are remaining, I'm going to simplify that one. It's 1 out of 25 chance on this one. So that will be the probability. We'll multiply these. And this is the essence of conditional probability, because these probabilities, the ones that are different, we could write that as the probability to draw a king. Given that we already drew a king, it becomes this one. And then that's the one again. We would be looking at probability to draw a king. Given that we already drew 2 kings, and we could be a little bit more descriptive in here of what it's talking about, but you know what this means. Probability to draw a king given that we already drew 2 kings. I'm just going to write it like that. It became 1 out of 25. And these are our conditional probabilities. And then when we multiply all of them, we would get 1 out of 13. I'm going to have to use some parentheses here. 1 out of 13, and then we're going to go times. The next one was 3 out of 51. Oh, that was actually possible to reduce also. It becomes 1 out of 17. And then we could have the last one, 1 out of 25. Either way, we'll get the same answer, which is that it is quite a bit less likely to draw 3 kings without replacement. And it becomes 1.8 times 10 to the negative 4th. So I'm going to call that 0.0002. Round up the 1 to a 2. And then we can do these from a table as well. It's pretty common to have these kinds of questions coming from a table where we are looking for what are the conditional probabilities or probabilities of different things. We've done table probabilities before, but not in a conditional case. We still have to just interpret the notation. And so that can become a big point anyway in any math classes, understanding what the notation means. Here, the probability to randomly pick a male out of this survey is a survey of people. What is their marital status? We sampled some males, we sampled some females. If we wanted to find out how many people were in this survey in total, we would need to add up all the males, and then we need to add up all the females, get some total over here. And actually, we're going to need those totals to do these probabilities. So I'm going to go 40.2 plus 62.2, and then we've got plus 3 plus 10 more, and plus, I did not like my 0, and then plus 2.4. Those are, I'm double checking if those are the correct numbers, and that's 117.8. So they surveyed a lot of people. This must almost be the whole United States. It's amazing. So this, of course, it came from the Census Bureau. So this is something from a census, and this would become all of the adults. 34, I'm counting up how many females are in this census right here, plus 13.8, plus 30.2, 124.4. And then if we wanted some grand total, we can add these together. And in that case, we would be getting 117.8 plus the 124.4, 242.2. And now we've got all the numbers that we could possibly need, even though it would be convenient as well to come up with these totals, like how many people said they're not married, how many people said they're married in total, because we might need some of these, even though we'll just take it on case-by-case basis, which ones we need for this problem. So the probability to randomly select a male, it should be the number of males divided by the total number of people. And so we already need that. These numbers that we came up with, there's 117.8 males out of the 242.2. And if we get that probability, we will have 0.486. I'm going to round that one to a 4 right here. 486 rounded up to a 4. 4864. The probability that somebody is divorced, what we want is the number of divorced people divided by the number of total. And so the number of divorced people, we do need this total. Luckily it's plus 10, so it's 23.8. Easy to get that one. So we need the 23.8. This is how many divorced people there are out of the 242.2 million. So it should be this probability. And that one is going to be 0.098. Have to round up this 2 to a 3, so 0.0983. And then we have an OR probability. So this one, when you see OR, you're thinking addition rule. So we should have the probability. First, why don't we check, because we might need to do the special addition rule, or in other words, the general addition rule. We have to either subtract the probability of and or not. And remember, that's in the case where these ones are not disjoint. So we got to check, are separated and female disjoint events? It doesn't seem like it would be. There must be some separated females. And so, sure enough, 3.2 people are separated and female. So this is going to be the probability of separated plus the probability of female minus the probability of being both separated and female. And so we should add up separated people, which are, we add these together, that's 5.6. We add up the females, we already had it, that's this number, the 124.4. And then the people who are both are the 3.2. So we're going separated people, 5.6. And then adding, I'm going to do these all out of the total. So here we can do each one of these as, probability that somebody is separated is 5.6 out of 242 million. If we do the probabilities, I'm just going to stack it down here, running a little bit out of space. But the separated people, if we just do this probability, that's 5.6 out of the total 242.2. The female people are 124.4 out of the 242.2. And then separated and female, that's 3.2 out of 242.2. But since we're adding and subtracting all this stuff, we can just look at the numerators and then do it all out of 242.2. So that's how I'm going to do this one. I'll actually go with some parentheses at the beginning. 5.6 are separated. And then we have 124.4 are female. And then we subtract the ones that are both, which is 3.2. And I'm going to make that out of 242.2. And so it's 52 point, or I was going to say it as a percent, but 0.5235. And then divorced or male, it's going to be the same kind of a deal. We need the divorced plus the males minus the people that are both, and then out of the total. We can do a simple calculation like this one. So the divorced people, there are 23.8 million in total who are divorced. The number of males is 117.8. We take away the people who are both, which there are, it was this one. 10 million are both male and divorced, so we take away 10. And then we're doing that out of 242.2. And so 54.3, have to round this one up to a 4, and that's going to be as a percent, or else as a decimal, 0.5434. 0.5434. Okay, so those ones are a review. We've already seen those before. What about now some conditional ones? Probability to be female given that you're married. Female given married. So we know that we're looking just out of the married people. It's given that they're married already. So we're looking just right in here at the married people, which there are 124.2 of those are married. So we're looking out of those, and what's the probability to be female given that you're married? We're just looking only in the married column. The females are 62. So there's 62 married females, and we're getting this probability 62 out of 124.2. And so we're looking at the married people. There's 124.2 million of those. 62 of them are females, so we get this probability, which is, I want 0.2. Was I doing out of, it's the other one is 0.2, because this goes 0.4. 124.4. I see. I confused myself. These numbers are so similar, the 124.4 and the 124.2. And so this one, these are the number of married people. 62 million are female. 0.499. Got to round it up to 2. 0.4992. And then probability never married given that you're male. In that case, we're only looking in the male column, all of these people, which there are 117.8 million of those. So we're looking out of the males. It's given that the person is male. We want to know what's the probability they were never married. So 40.2, that's how many never married people there were. 40.2 in the male column out of 117.8. So 40.2 out of 117.8. That's 0.3413. 0.3413. Probability to be male given that they're separated. So we're just looking only in the separated row. It's given that they're separated. So we're only dealing with 5.6 million total people. We want to know the probability of male. There's 2.4 million males separated. So 2.4 out of the 5.6, which is going to be, as a decimal, 0.4286, rounding this one up, 0.4286. And that is everything to consider for conditional probabilities. Just to see what happens to the multiplication rule, in this case, I'll write down the general formula for it. Whenever we have the probability of E and F, this is when the multiplication rule comes into play, which is when we are dealing with an AND situation. We should multiply, but what we have to do in general is multiply the probability to get E, because we want these both to happen. So E happens, and then F happens, but it should be given, probability of F, given that E already happened, because the event E happens, and now we want to know what's the probability that F happens given that E already happened. And when they're independent, then this is just the probability of F, because these two things are equal whenever F and E are independent. E happening doesn't change the probability of F if they're independent, so it just becomes probability of F right here. And that was the special multiplication rule, which is that you can just multiply the probabilities. If we don't know if they're dependent or not, then the general way of writing it is like this, because this may affect, in the conditional case, may affect the probability of F. And so this is the general multiplication rule. General multiplication rule goes this one. Okay, and then there's a very famous problem. It's called the birthday problem. It's asking this question, and something kind of funny to do in a group of people, because it seems like it'd be kind of rare for people to share birthdays, which it is rare for just individuals. You have a 1 out of 365 chance to share a birthday with just any random person. But it turns out, and I don't want to cover it in this video, it's a little bit in-depth how to actually do this probability calculation, but this one right here, it's something interesting to look at. You can look it up. if you want to learn more about it. But it turns out, and perhaps we can revisit this in Chapter 6, because this is a binomial probability kind of situation. But if you're in a group that just has 23 people, there's a 50% chance that 2 people share a birthday in there. It's kind of an interesting fact from statistics. But anyways, that does it for the 5.4 video, and I hope this was helpful to you. I will catch you in the next one. Thanks.